Okay, Mr. Isaac here. I'm going to try to talk you through section 5.3 of your book. Probably the most important section, certainly of chapter 5, but may even be the most important section for really all of the physics that we would study this year. When we're dealing with conservation laws, which is what this section is dealing with, it becomes a really powerful way of looking at the world around you. So read through these learning targets. We'll talk about the homework at the end of today's lesson. This cartoon here just to introduce the topic of energy conservation. Apparently he's not lazy, just doing a bit to conserve energy. The idea here is that you've heard of the conservation of energy. All energy in the universe is a constant. You cannot create or destroy energy. It just changes form, but not in total quantity. So a funny cartoon to introduce the topic. So from your reading, what does it mean? What does it mean to say something is conserved? And really what that means is that to be conserved just means to remain constant or unchanged. Now, technically speaking, we can change quantities that are conserved can change in some ways, but they don't change in amount. So conserved quantities can change in type, but not in amount. Some examples of quantities that are conserved. From your reading, you probably read that that mass is a conserved quantity. When you break a light bulb, the amount of mass that that light bulb has does not change when you break it. It just changes shape and it shatters, but if you add up all these things, put them on a scale, it would have the exact same mass as that light bulb that's intact. Now over here, there are cases in which energy, specifically a certain form of energy that we'll talk about next, where energy is conserved. And this person here, it's a skateboarder, moving along at position 1, and this person has, what form of energy do you think they have here? And if you said kinetic energy, you're correct. So the person has KE because they're moving. This pie chart, the blue portion of that pie chart, would represent the person's kinetic energy. And if you were so inclined, you could figure out exactly what the magnitude is, 1/2 mv squared. Now, as they move along this ramp, you can see at position 2, they're at an elevated position now. And sure enough, you can see that their kinetic energy has become smaller, so KE has become less. And something else has increased, and if you're wondering what that form of energy is, I bet you can tell me. It's gravitational potential energy. And in this case here, the change that it had in kinetic energy is exactly offset by the change that it had in gravitational potential energy. So this became smaller, that became bigger. And certainly as they continue to rise, they move slower, but as they move slower and their kinetic energy becomes even smaller, their GPE increases. The idea of energy conservation is that the total energy stays the same. Now, before we can get into any problem solving, we have to talk about this thing called mechanical energy. So what is it, and why is this classification useful when describing physical processes? This is just a picture from your book. It's a breakdown of how we can classify energy into 2 main forms. Mechanical, which is what this section is about, and then non-mechanical. Now, the main difference between these is that mechanical deals largely with big objects, so large scale kinds of things. So most of the physics class that we've been looking at so far has really just been dealing with objects that are on the macroscopic size. So things that you can touch and feel, baseballs, bowling balls, cars, you name it. Wrecking balls, you name it. Over here, non-mechanical energy is usually dealing with things that are closer to the subatomic portion. So it may be at the atomic or subatomic level. So you could be talking about chemical potential energy. So I'm just going to abbreviate that. Chemical potential energy. You might have solar energy. So maybe you might think of that as just light energy, nuclear energy, stuff like that. Let's see, how about thermal? I didn't spell nuclear, right? Thermal energy. Thermal energy is really just what we would call heat, but these are non-mechanical. Now, the reason mechanical energy is a useful form of energy is that there are many processes in which mechanical energy is conserved. And we'll talk specifically about when those processes, or what has to be the conditions for those processes to conserve mechanical energy. Let's summarize what mechanical energy is. It's really just the sum of the kinetic and the potential energies that are large scale. Now we can say that with some things that I have hidden behind here. This looks pretty ugly to begin with, but it's really not too bad. In objects or systems, mechanical energy is the sum of its KE, GPE, and EPE. Written as an equation, it looks a little bit confusing. It means mechanical energy is equal to the kinetic energy of an object plus the sum of its forms of potential energy. And since potential energy can be either GPE or EPE, this could be both of those things, or it could be only one, or it could be neither. It could just be an object that's moving, but it's not elevated and it doesn't have any elastic potential energy. So whatever its sum is, that's what we call mechanical energy. It's useful again because in some basic physical processes where outside influences such as air resistance, friction, and so forth, where they're negligible, we see that mechanical energy is conserved. Now, this picture here is just showing a ball being tossed up, and we all know when you throw a ball up, it eventually reaches the top and comes back down. This is just showing that the object's KE, which is what it has here, gets converted into GPE, which it has here, and then it gets back converted into KE here. At any point, and by the way, here it has both KE and GPE. And the idea of mechanical energy conservation is that if it starts with 10 joules here, it might have 5 and 5. Up here, it's all 10. Back here, it's 5 and 5. And then it's back down to 10. Just different forms of energy. Now over here is a little bit more involved. Here I have a ball that's moving, so it's got kinetic energy. It's elevated, so it's got gravitational potential energy. And it could even have elastic potential energy, which it does here because it's got a spring that's compressed. Now as this ball travels through the air and then falls back down here, let's look at what's happening right here at the very top. Now the spring is not going to discharge here. We're going to keep that spring nice intact. But the kinetic energy is going to become smaller as it rises. Let's say that the kinetic energy has reduced to 8 units right at this particular point here. So we're going to look at the energies that exist at the apex. If the kinetic energy reduced from 12 to 8, then the gravitational potential energy must have increased from 7 to, what do you think? And if you said 11, you're correct. Because whatever the kinetic energy decreases by, the gravitational would increase by. And so 8, 11, and I still have 9 for the elastic potential energy because that hasn't discharged yet. And you see that I still have the exact same amount that I had here. And I forgot to add those up, but you can see that the 28 units is still 28 units. So mechanical energy just changes in form, not in amount. How do we take the idea of conservation of mechanical energy and apply it to solve problems? Well, we're going to start with just a table to illustrate how mechanical energy is conserved. An egg is dropped in the name of science, falls off the table, the countertop, lands on the floor, and is cracked. Well, if we look at any point in its motion here, we can see that the sum total of the mechanical energy is a constant here. It starts out at 1 meter above the ground. It's a 75-gram egg, so we could compute the gravitational potential energy. It's not moving, so it's got 0 speed, it's got 0 kinetic energy. At any other point during its fall, we can choose any one of these things. We can see that as the height is getting smaller, the speed is increasing. GPE goes down with the height. Speed goes up, or KE goes up with the speed. We still have the exact same mechanical energy. Now down here, a wrecking ball converts PE into KE, and then KE is used to do work. During this process, mechanical energy is conserved. So I'm just going to write that like so. Mechanical energy is conserved. Now, mechanical energy is not conserved in this process. And the reason it's not conserved is because we have some external forces here. We have that wrecking ball is exerting a force on that wall. It's doing work on it. Well, during that work that's done here, we don't have mechanical energy being conserved. We're actually using the mechanical energy of that ball to be able to do work on that building. So understanding when mechanical energy is conserved and when it's not conserved allows us to be able to use the conservation laws at the appropriate times. Why can we use mechanical, or why should we use mechanical energy to solve problems? Can't we just analyze motion using the Fab 4 and Newton's second law? And the truth is that you can do this at times, but if you recall, the Fab 4 was only good when the acceleration was constant. Well, what if the acceleration is not constant? So this is for constant A. Well, this is not a constant acceleration. As that roller coaster goes over that hill, its acceleration is variable. It's got a different rate of acceleration the entire time because we have a variable slope there. I can't use the Fab 4 equations to analyze this, but I can use conservation of energy. A ripcord ride, popular at amusement parks. I know Michigan Adventures has one of these. This is a variable acceleration. We have a weight force acting down, always down. A tension force that is constantly changing direction as they swing throughout its motion. So we have a variable A here. Cannot analyze this using the Fab 4 and Newton's second law. It would be really tough, but we can do it with energy conservation. And last but not least, I wanted to share with you a discussion about projectile motion. This was a confusing topic in trimester A, and I just wanted to show you how much easier it is to analyze using energy. Let's say I have a projectile that's launched from a building 35 meters up. It's launched horizontally. It travels 80 meters. Don't worry, I'm not going to ask you to determine its speed and all that kind of stuff. We did that in the first try. But how does its speed here compare to the speed here if instead of it being launched at an angle, it's launched up at instead of it being launched horizontally, what if I launched it at an angle at the exact same speed but at an angle here? And if you're thinking that these speeds are different, you would be wrong. The speeds at which they hit would be exactly the same. And I can do that and understand it via energy conservation. If the mechanical energy initial is exactly the same, then as this ball rises and falls, or as this ball just simply falls, the total mechanical energy would stay the same. So whatever it starts with is what it ends with. It would have the exact same amount of mechanical energy at the bottom as this one, because they start with the same amount of energy here. Now, this conversion takes place a lot quicker. It changes from, let's see, what forms of energy are present here? It's elevated, so it's got GPE, and it's moving, so it's got KE. Well, it's got two forms of energy here. Down here, it really only has kinetic energy if I call this my reference position. So all of its loss in GPE goes into KE, and it has the exact same size of the pie that it had up here. Now down here, what happens, or on this one, is it starts out with the same GPE and the same KE. It's just being shot up at an angle. It goes up and it converts its KE into more GPE up here. But we still, as I gain GPE, I lose KE, and then it goes right back down. At this spot, it has the exact same amount of energy in each form as it had here. It's just moving in a different direction. And remember, energy has no direction associated with it, so its velocity is not any different here, its kinetic energy rather, is not any different here than it is here, because kinetic energy is scalar. And then as it falls down through here, it has the exact same amount of energy as it started with, just in different forms. So their speeds have exactly the same. By the way, their GPE at this spot is 0 in either case, so all of the energy is now KE. And since kinetic energy depends on mass and speed, and the masses were the same, their speeds would be the same. Now that can be analyzed fairly easily conceptually with mechanical energy conservation. Trying to do this with the projectile motion equations would have been really tough. So motivation for you on learning to solve problems dealing with energy conservation. Now, I did things all conceptually so far. I'm going to give you some problems to try just to see if you can do them. These are fairly straightforward conservation of energy problems. I'm going to give you a chance to try those and see if you can do those before I give you examples. I am going to go through and spend a lot of time looking at more complicated examples, but let's see if you can try those problems and just see what you can do with them. Okay, that's all we have for today. Go Bucks.